Hi everyone, my name is Michael Schröder and I'm a PhD student at TU Wien in Vienna, Austria. Last year I spent some time in Cambridge at Microsoft Research where I worked on discovering interdependencies between feature flags in a Microsoft Office codebase. Feature flags are a design pattern to conditionally enable a code path. They are used to run experiments in production like A/B tests, to roll out features in a controlled manner, or for emergency bug mitigation. When feature flags are nested, like in the example on this slide, they become interdependent. This means that the dynamic runtime value of the parent flag determines whether or not the child flag is queried. Such interdependencies can easily extend beyond function, module, or even process boundaries. Here's a real example from the Microsoft Office codebase showing an interdependency between two feature flags that spans multiple files and additionally involves C++ templates and macros. Here is another example from the Office codebase showing a feature flag relationship that exists entirely inside an XML resource file used to construct UI elements. The Microsoft Office codebase contains about 12,000 active feature flags, with flags being added and removed nearly every day. Developers often are not aware that some flags are interdependent, and these unknown interdependencies can be and have been the source of serious bugs. One way to mitigate these bugs would be to test all possible combinations of feature flags, but this is simply not feasible at this scale. So the goal of our work is to automatically discover these feature flag interdependencies, and to this end we developed a novel approach that allows us to infer such interdependencies by using probabilistic analysis of feature flag query logs. We're able to achieve over 90% precision with this approach while recalling non-trivial indirect feature flag relationships across different source files. The examples I've just shown you have in fact been found using our approach. So, how does it work? In Microsoft Office, anytime a feature flag is queried during the run of an application, this query is logged, together with the current value of the flag. Typically, this value is a boolean, but not necessarily so. Here is an example of a collection of such query logs, where each of these segments is an independent run of the same application. In the first step, we try to discover co-occurrences between the feature flags. Intuitively, if two feature flags are related, then we would expect them to be queried within some time window of each other, and we would expect this time window to be roughly the same across different runs of the same application. So we can drag a sliding time window across these query logs and collect all feature flags that co-occur within that time window. At the end, we have a co-occurrence graph describing a maximal set of possible feature flag relationships. Note that the edges in this graph are directed because we take temporality into account. If some feature flag is queried after another feature flag, then it cannot be its cause. However, this is not yet a causal graph. In order to make it into a causal graph, we have to eliminate all relationships that are clearly non-causal. We can do this using some basic reasoning. For example, we observe that the feature flag C here is queried regardless of the value of the co-occurring flag A. C is queried both when A is true and when A is false. The value of A has no actual influence on whether or not C is queried. Thus, there is no causal relationship between these two flags. Next, even though we know that C is only queried whenever B is false, we actually have no information about what happens when B is true, because we have made no observations of B when it is true. In this case, we do not have enough information to make a causality judgment, so we eliminate this edge from B to C and assume they are not interdependent. Finally, we do have enough information to determine that A might be the cause of B, because we see that whenever A is true, it co-occurs with B, and whenever A is false, it does not co-occur with B. In the end, the causal graph is simply A causes B. Unfortunately, in the real world, it is not quite as simple. Here is a typical instance of a real-world co-occurrence graph. Naive causal reasoning would require us to eliminate all of its edges because they all contradict one another. But not all the occurrences in this graph are equally valid. Some of them are merely noise. Noise can appear for any number of reasons. There might be bugs in the logging pipeline where occasionally queries are dropped or duplicated or the time ordering gets mixed up. We might get crossed signals due to a set of logs spanning multiple apps or app versions. There might be code drift during the time that we collect the logs, and sometimes there are simply coincidences where the data just lines up in a way that is indistinguishable from a real signal. Since we can't eliminate all sources of noise and we can't use naive reasoning on noisy data, how then can we know which relationships are actually true causal relationships in a real-world setting? To answer this question, we can borrow some notions from probability theory. We can actually calculate the likelihood that some feature flag B will be queried if another feature flag A was observed with a particular value, based purely on the number of occurrences and co-occurrences of these flags in our logs. Similarly, we can calculate the likelihood that some flag A had a particular value when it was followed by an observation of B. These are just regular conditional probabilities. Using these conditional probability formulas, we can now ask ourselves, what are the expected probabilities of a real causal relationship? What would we expect to see if there was an actual relationship between two flags? The simple conditional if A then B is the Platonic ideal of a causal relationship. Clearly, the likelihood that B will be queried if A is true is 100%, while the likelihood that B will be queried if A is false is 0%. Similarly, the likelihood that A was true when B is queried is 100%, and the likelihood that A was false when B is queried is 0%. Realistically, however, A or B might occur multiple times in the source code, possibly in relation with other feature flags. The probabilities will then be affected by some values proportional to the number of those other occurrences. So if A has other children besides B, then the probabilities will be diminished by some unknown factor proportional to the number of these other children of A. Similarly, if B has other parents beside A, then another unknown factor proportional to the number of these other parents of B further diminishes some of the probabilities. Now, while these unknown factors are different for each particular combination of feature flags, it is reasonable to assume that most feature flags have only a small number of different parents or children, and thus the unknown factors are expected to be significantly smaller than 1 on average. So we can expect approximately this pattern of probabilities for a real causal relationship between any two feature flags, where the parent flag needs to be true in order for the child flag to be queried. If the parent flag needs to be false, then we would expect to see the inverse pattern. And so we have different probability patterns based on different scenarios that are possible for a causal relationship depending on the different values that the parent flag can assume. Knowing these expected probabilities, we can now tackle the noisy real-world co-occurrence graph that we saw earlier. First, we calculate all possible conditional probabilities between all feature flag observations. Then we can simply compare these with the expected probabilities. If one of the patterns matches, give or take a small error value, then that scenario is the most likely. Here we see that the most likely scenario is that A is a causal factor of B. Specifically, A having the value false will cause B to be queried. The expected values for this scenario have a combined error of only about 5% compared to the actual observations, which is the lowest error out of any of the possible scenarios here. Formalizing this notion and generalizing it to non-Boolean feature flags, we can compute an error value for each possible relationship between any two flags A and B based on the different values the parent flag A can have. We can then take the minimum error across all of the possible scenarios as the overall error E for the possibility that A causes B. We additionally compute a kind of confidence value n based on the absolute number of observations that contribute to the error calculation. If our error value is very low, but it is only based on a handful of observations, then we might naturally not be as confident in the assessment. Putting it all together, we are finally able to say that A causes B if we observe A with at least two values and the overall error is below some empirically determined threshold and our confidence in the error is above some threshold. So how effective is our approach? It turns out very effective. This graph shows our precision, meaning how many of the relationships that we discover are actually true relationships, plotted against different values for the error and confidence thresholds. Choosing an error threshold of 0.25, we can achieve 90% precision. Increasing the threshold lowers the precision as expected, and we have a baseline precision of 66% due to the co-occurrence discovery stage already filtering out many impossible relationships before we even applied the probabilistic reasoning. The paper contains more information on our evaluation procedures and also includes a discussion of recall, which we believe to be non-trivial. Also in the paper, we present a first analysis of recurring patterns that we could identify in the interdependency graph of an application. We believe these could be used to find areas of unusual complexity or risk. This is all that we have time for in this short presentation. If you're interested, I encourage you to read the full paper or contact me for any follow-up questions. Thank you.